Okay, so in 2.5, we're looking at the domain of a function. So think about the graphs when we were looking at the graphs of these functions, what these look like. It's all of the possible x values. If any value causes x to be 0 in the denominator, it cannot be part of the domain. Okay, for a radical function, you set all the values underneath the radical greater than or equal to 0, and then solve. So let's think about what these look like here. So I'm going to look at my first one, f of x equals 3x plus 12. This is just linear. We can look at these in our graphing calculator as well. If you go to this button up here, where my mouse is circling, it says y equals. Okay, and then you enter that in. So 3, and then here's your x button. It is next to alpha on the right. Just hit that. It'll have an x, and then plus 12. And then you can hit graph. And that's just a straight line. So it's going off both sides of the graph, which makes that domain all real numbers. So negative infinity to infinity. So anything really that's linear, okay, we're going to circle this, we're going to write linear. Okay, that domain will always be all real numbers. Okay, unless it's a vertical line, then it won't be. But everything else. Now, in number 2, we do have something that could make the denominator 0. So I want to show you guys what this graph looks like. So if I come back to my calculator and I hit y equals, and I'm going to clear this. So the way I'm going to enter this is like so. I'm going to do 5 divided by, there's more than one term in the denominator. So I'm going to go parentheses and then x. Remember the x is to the right of the alpha, plus 3. And then close the parentheses. So the whole denominator goes in parentheses. And then here's this graph. So what's actually happening here is I'm coming from the left, from negative infinity, and I'm going and approaching this value right here. This line here is not actually on the graph. Some of you might not actually have it. Yeah, and that's because I have them turned on my graph, and you might not have yours turned on. It's called an asymptote. It's a hole in the graph. Okay, because this is at negative 1, 2, 3. If I plug negative 3 into this equation right here, I'm going to get 0 in the denominator. Okay, so I approach negative 3, then I start up here from negative 3, and I go to the right. The reason why is because, look at this equation. If I plug, and I said x equals negative 3, if I plug that into here, I would have 5 over negative 3 plus 3. I'd have 5 over 0. Can I do that? Cannot do that. Okay, no zeros in the denominator. So I can't have that. That is a hole in my graph. So these holes are going to be notated in the domain, but they're called asymptotes, which we're going to look at, I think, at the bottom of this page. I just want to show you one more thing on the calculator. So where you have the word graph, if you hit second graph, you're going to have a table. That's going to give you a table of values. If I plug these x values in, this is what the y values will be. If you scroll up to where it says negative 3, you get an error. Because again, if I plug that in, I get 5 divided by 0. Okay, so you can also confirm what that value is on the table of values. But generally, the procedure for this, when there is an x value in the denominator, take the denominator, set it equal to 0, and then solve. You get x equals negative 3. You know that x cannot equal negative 3 because that would give us a 0 in the denominator. So it tells us the whole. So the way you write the domain goes like this. Negative infinity to negative 3, parentheses, the union symbol, negative 3 to positive infinity. Okay, so we're going all the way to 2.999999, negative 2.99999, but we're not actually going to, okay, because that would give us the whole. All right, number 3, this graph is a quadratic. Okay, what does it look like? It looks like this, right? So it's going to always have a domain, same as linear, negative infinity to infinity. Now, number 4, there is an x value in the denominator. So we want to find where those holes are. So you take the denominator, set it equal to 0. So x squared minus 4x minus 5 equals 0. So you can do that, or you can look at the graph. Either way is fine. This one I would factor. What would this factor to? I'm thinking this is x minus 5, x plus 1. And that would give us x values of positive 5 and negative 1. So those are the holes. So put a line through your x equals sign. Okay, now on the domain, you're going to go left to right. So if I'm coming from negative infinity, am I going to get to the 5 or the negative 1 first? The negative 1. So I'm going to go like this. Okay, I'm going to go from negative infinity to negative 1, union. Then I'm going to go from negative 1 to 5, because that's the next value I'm going to hit, union 5 to infinity. And let me show you what this looks like. So if we put this in our calculator, go back to y equals, and clear that, we're going to go 28 divided by, then parentheses, then you have x squared minus 4x minus 5, close parentheses. Okay, then hit graph. Okay, so we're going from negative infinity to negative 1. Okay, here's the asymptote at negative 1. Then I go from negative 1 to 5, and then from 5 to infinity. Now, if you don't have a graphing calculator and you want to look at these on your computer, there's a website, and it's called Desmos.com, D-E-S-M-O-S. I'm going to pull it up here as soon as I can find my mouse. Here it is. So Desmos, and there's an app on your phone for this as well. Okay, the only thing is you can't use it on a test. You have to have an actual calculator. So if you hit graphing calculator, we could put this in. So here I would type this in, 28 divided by, and then you hit the keyboard thing here. Yes. I do not encourage Mathway. Okay. Yes, Mathway gives you a false sense of security. Okay, so underneath here, you would do x squared. Here's the squared button. And then it was, what was it, minus 4x? Yeah, minus 4x minus 5. And then there's the graph. And you can zoom out. And it's very, very user-friendly here. So you can use this as well. I like this one better than the calculator because it's a It's easier to see and play with. And you can also get the table on it if you just hit the settings, the edit list, and then table. And then you've got these values here. So it tells you the X values. The only thing is you've got to like actually enter them in if you wanted to check. So like this just goes from -2 down here. So let's say I want to know what it is at 5, just to check. I'd have to actually manually put a 5 in, and then it would tell me. So you can and you can play around with that with the table. And just to go back, you would just exit out of that. Oh, actually, I think you would hit the back button. Something like that. I don't know. Play around with it though. But this is a nice graphing tool as well. Okay, so number 5, we've got values in the denominator. So it's very similar to number 4. Okay, you're just going to take each of the denominators and set them equal to 0. So you have x minus 4 equals 0. That would give you x equals 4. And then x plus 6 equals 0. X equals -6. Now we know if we had those values in either denominator, you would have a 0 in the denominator, making the function undefined. So put lines for your equal signs. And then you're just going from left to right. So you're going negative infinity. You're going to run into which one first? -6. Union, -6 to 4. Union, and then 4 to positive infinity. All right, and then number 6 is a square root function. So what we're going to do with the square root function is you're going to take whatever's under the square root, set it greater than or equal to 0, and then solve it. So x is greater than or equal to 1. And we would write that in interval notation like this, bracket, 1 to positive infinity. What does that look like? Do the Desmos again. We've got square root x minus 1. There you go. So it's like, it almost looks like the square root part, kind of like a check mark, almost. All right, transformations of functions. So on your homework for the transformations of functions, you're going to be checking, there's just going to be a list of things, and you're going to check like vertical shift, horizontal shift, etc., etc. When we're talking about transformations, we're talking about a transformation from the parent function. The parent function is just this here, y equals x. Or if it were x squared, y equals x squared, okay, with a y-intercept of 0 and a slope of 1. Okay, so how did these change? Now, sometimes it's not from that. So this example here is actually not from that one. We want to know if this is our parent function, we want to move that. So here's the general way to go about this. You have a parentheses x minus h plus k. Okay, a would be a change in the slope. So that would be a vertical stretch or a vertical shrink. Okay. H represents a horizontal stretch, so that's going to be going left to right. K represents a vertical stretch, so that's going to be going up or down. Okay. F of negative x is the function f of x reflected across the y-axis. So for the first example, this is the function f of x, is what they're telling you. And they want to take this and make a new function g of x, meaning take f of x and then subtract 2. So because this is not inside parentheses, this is a k value, which means it's a vertical stretch or a vertical shift. Sorry, shift here. Okay, and it's -2, which all this means is I'm moving the function down 2. So 1, 2. The actual process of doing this, the line thing is really bad on here. The actual process of doing the stretching and the shifting, transforming, is really easy. Naming what the transformations are gets a little tricky. Okay, so all this we check off the box. This is now g of x. Is we had a vertical shift -2 or down 2. So we'd have a box, we would check it, vertical shift -2. Okay, let's say, for example, we have the function y equals x. I could get this to actually go. Okay, so this is the function y equals x right here. And let's just say you have this function here. Okay, so all that's happened in this function is I've moved it. It's got the same slope. Okay, all I've done is I've moved this part up 1, 2, 3, 4, 5 points. So all I would do here is say that this is y equals x plus 5. And if I were naming it, that would again be a vertical shift up 5. Okay, so let's look at another example here. So here's f of x on this graph. And what we want to do is we want to do g of x, and we're going to make that f of negative x plus 3. So the first thing you're going to take care of is the negative x, which means you reflect it across the y-axis, which means this. Okay, so I'm going to take these points, and I'm going to move them across the y-axis. This is symmetrical, so it really shouldn't be too bad here. So this is, let's see, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. So I'm going to move this guy over here to -6. This one here to -5. Okay, and then the points got to come over here. So this was 1, 2, 3, 1, 2, 3. So 3.5, 3. So go across here, -1, 2, 2, 3.5, 1, 2, 3. So right here. Okay, so we're looking like this. And then this point is -1, 2, 3.5, -2. So 1, 2, 3.5, just about right here. So we're going to go down to here. Okay, so that is the reflection. And then you're going to move it up 3. So you're just going to move every value up 3. So we'd go up 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, about right there. 1, 2, 3. All right, so looks like we'll go with bright green here. So we're looking like this. There's your function. Okay, so you first reflect it across the y-axis. I guess it didn't have arrows to begin with. First reflected across the y-axis, and then you move it up 3. So for these ones, you would either name the transformations, probably both actually, check off naming the transformations, and then picking the graph of what it's going to look like. And that would be g of x. And I put that there so we could do another one, or that one over here, but I did it all on the same graph, so just ignore that second graph there. All right, so then example 3, we're going to graph the function, and then we're also going to do the transformations that happened for these functions. So this is going to come from the parent function y equals x squared, because it's starting as a quadratic. So y equals x squared is going to look something like this. Okay, that's y equals x squared. That's the parent function. So what shift is coming about from this? Okay, let me draw arrows. Okay, so first of all, you've got this -3 vertical stretch or vertical shrink. So what's actually happening here is it's getting, with the -3, it's going to get narrower because of the slope would get narrower. I always get these ones confused. It is a stretch. Think about a rubber band. I'm stretching the rubber band to go up here. So it's a vertical stretch of -3. Okay, we're going to take care of that in a second. This here, this shift inside the parentheses, that is a horizontal stretch. Okay, so left or right, when you look at it, okay, look at the sign. It's x minus h. So we're just doing the h. So it is to the right 3. It's a positive. So you're going to pull out the opposite sign out of the parentheses. This is going to go right 3. And what's going to go? This point here, the vertex of your parabola. So 1, 2, 3. So right 3. And then you have a plus 5. So that would be an up 5. So take that point and go up 1, 2, 3, 4, 5. It's going to get narrower by -3, so it's actually going to be facing down. So it's going to look something like this, probably pretty narrow, really bad at drawing, but let's look at what this actually looks like. Okay, so if I go to y equals, I'm going to put this in. So I have -3, then parentheses, then you have x minus 3, close parentheses, squared, plus 5. Squared is up to above the 7 to the left. Okay, then hit graph. Okay, so that's what we look like. So my drawing is bad, but I was close. Let's look at it again. All right. So we have this point here. We've got a vertex at 3. 1, 2, 3, 4, 5. And you're looking something like that. And that is from the parent function. Y equals x. So when we're naming the shifts, okay, first of all, this is reflected across which axis? Yeah, so reflect across the x-axis. We had a horizontal shift, right 3. Or positive 3. We had a vertical shift, up 5, plus 5. And then we stretched the graph. By 3. Okay, so you're either going to shrink or stretch the graph. Thinking about the rubber band, what we do with the rubber band. Okay, so those would be all the things that we would check off on that. Okay, so look at example 4. You've got the function square root of x plus 6. So if you think just square root of x, remember that one is just the check mark. So square root x, there's your graph. So all this is that's just up 6. Okay, and you could actually pull these both up on your calculator. If you just scroll down, you can put them both in at the same time. So square root, and then it would be x, close the parentheses because the plus 6 is not under the square root, plus 6, and then graph. So it's the same graph. All it is a vertical shift up 6. So we'd start up at 1, 2, 3, 4, 5, 6. Just looks like that. So it would be from here to here. This would be your new function. All it is a vertical shift up 6. Okay, so really you guys are supposed to have a graphing calculator. Really use those to your advantage. Visualize what's going on, and then you can see the shifts much better. So if we take a look at this one, again, this is x squared. Okay, so your parent function is a parabola, 0, 0. Let's put both of them in here. So you've got, for the first one, x squared. Then scroll down. Then we're going to do 3 parentheses, x minus 1, close parentheses, squared, minus 2. Graph. Okay, that's x squared. There's our other function. Okay, so we're shifting, looks like to the right and down. And then also, I'm stretching that. Okay, so we had, let's see, it was to the right 1, down 2. So here is my new vertex. And pretty tight there. So very thin, something like this. It's really bad. Okay, but that's what the graph's going to look like. Let's name what happened. Okay, so we are doing a stretch 3, so that's your stretch. I think it's called a vertical stretch. We went to the right 1, we had a horizontal, positive 1. We went vertically down, so down 2, so vertical minus 2, and that's it. We didn't reflect across anything, so we should have 3 things for that one. Okay, let's take a look at example 6. So if this starts from the square root function, okay, looks like we're gonna have a horizontal shift here with the minus 3, vertical with the plus 2, and then that is going to stretch as well. So if I put this in, y equals, let's clear these. Okay, so the first one is just square root x. Close that. Scroll down. Then I have 3, then square root x minus 3, close the parentheses, plus 2. Okay, then hit graph. So there's my square root of x. There's my next one. Kind of floating out there, but that point there, 1, 2, 3, 1, 2. So we're getting that from my h and my k here. So here's where we start. Then you had a horizontal 1, 2, 3, vertical 2. So we're starting right here. And then it kind of just went almost straight up, kind of like that. Okay, so this will be my horizontal shift. And that is +3. Vertical, I also went up, so that is a +2. And then I stretch by 3. Yes, question. From here, when I look at the function, it starts. When I look at this function here, it is starting with a squared in it, so the parent function is x squared. If it doesn't have a squared, it's just a y equals x. So if it starts with a squared in it, it's a parabola with the parent function. You're going to have, basically, you're going to have the 3 types. You're either going to have y equals x squared, or y equals square root of x. So those are the 3 you're looking. So if it starts without anything, it's just the y equals x. If it starts with a squared, it's the x squared. If it starts with the square root, then it's just square root of x. All right, so that is 2.5. We're going to shift to 2.6 with composition functions.